Hello, this is Dr. Holcomb. In this video, we'll be talking about alkenes and a class of reactions known as addition reactions. They're called addition reactions because a component such as HX adds across the double bond. The regiochemistry of the addition reaction is known as Markovnikov addition. Markovnikov's rule states that the hydrogen of HX adds to the carbon bearing the most hydrogens. In this case, then, the hydrogen of HBr adds to the carbon bearing 2 hydrogens, leaving the bromide to add to the carbon bearing no hydrogens. Markovnikov's rule arises from the formation of the most stable carbocation. Addition of the bromide ion to the tertiary carbocation then affords the alkyl bromide product. We can use Markovnikov's rule to quickly identify the major product of each of these addition reactions. Pause the video now and write down the product of each of these reactions. Each of the products adheres to Markovnikov's rule, with the hydrogen added to the carbon bearing the most hydrogens and the halide added to the carbon bearing the fewest hydrogens. Notice in the third example we get 2 stereoisomers. In this case, the bromide can attack from the top face or the bottom face. Both faces are equally accessible and 2 products are formed. See how quickly you can determine the Markovnikov product when hydrogens are omitted. Pause the video and determine the products. The first 3 products can be readily derived from Markovnikov's rule. The fourth product, however, is derived from a knowledge of the stability of the carbocation formed. The benzylic carbocation is the more stable of the 2 possible carbocations due to charge delocalization by the adjacent phenyl group. Nucleophilic attack by the bromide gives the alkyl bromide product observed. So in cases where Markovnikov's rule is indeterminate, use carbocation stability to determine product distribution. When the addition of a hydrogen halide to an alkene leads to a secondary carbocation, rearrangements may occur. In this case, the secondary carbocation undergoes a hydride rearrangement to form the more stable tertiary carbocation. Nucleophilic attack by the chloride ion gives the tertiary alkyl halide. This reaction then gives rise to a mixture in which the secondary alkyl halide and the tertiary alkyl halide are formed, but the tertiary alkyl halide is most likely the major product as a consequence of the rearrangement. For each of the following addition reactions, identify the major and the minor products. Pause the video now. In each of these cases, the minor product arises from Markovnikov addition. The major product arises from a rearrangement of the secondary carbocation. In the case of the vinyl cyclobutane, secondary carbocation rearrangement occurs upon ring expansion. This ring expansion relieves ring strain and forms a tertiary carbocation. Nucleophilic attack of the bromide nucleophile on the tertiary carbocation gives the bromocyclopentane as the major rearrangement product. Acid-catalyzed hydration of alkenes also goes by way of Markovnikov addition. The first step is addition of a proton to the carbon bearing the most protons. Water acts as a nucleophile and attacks the tertiary carbocation. Subsequent reaction with a base such as water affords the resulting hydration product. Note that each of these steps are equilibrium reactions. The principle of microreversibility indicates that we can go in either direction depending on the reaction conditions. Employing the principle of mass balance and running the reaction in water allows us to produce the alcohol product. The relative rate of the hydration of alkenes is a function of the stability of the carbocation intermediate. The greater degree of substitution on the alkene, the more stable the resulting carbocation intermediate, and the faster the ensuing reaction. Using the previous relative rates as a guide then, choose which of the following pairs reacts faster under hydration conditions. Pause the video now and pick which of the pairs reacts the fastest. Each of the fastest reacting components is marked with a check mark and an indication of the carbocation character. The phenyl derivative reacts faster because it forms a secondary benzylic carbocation, which is highly stabilized due to delocalization of charge. Given the preference for Markovnikov addition in the hydration of alkenes, how then does one prepare the anti-Markovnikov hydration product? The solution to this problem is a hydroboration oxidation sequence. The first step in the sequence is treatment of the alkene with borohydride THF complex and addition of borohydride across the double bond. The resulting alkyl boron complex is then oxidized with basic hydrogen peroxide, replacing the boron with a hydroxyl group. This reaction is regioselective and stereospecific. The regioselectivity is governed by the delivery of the hydride to the more hindered carbon. The larger boron atom is added to the less hindered carbon. The stereospecificity arises because the boron and the hydride are added to the same face of the molecule. Basic hydrogen peroxide affords the nucleophilic hydroperoxy anion which attacks the boron. The resulting oxyboronate species undergoes a rearrangement. The oxyborohydride that's formed undergoes further decomposition to form the alcohol product. The net result of the oxidation step is replacement of the boron with a hydroxyl group with retention of configuration about the carbon center. In addition to being stereospecific by virtue of the mechanism, the hydroboration oxidation sequence is also stereoselective and subject to local steric effects. In this case, the borohydride is delivered to the face opposite that of the bulky isopropyl group. The hydride is delivered to the carbon that is more sterically encumbered, and the boron delivered to the less hindered carbon. Oxidation replaces the boron with hydroxyl with retention of configuration about the carbon. Note, this is very different than the product formed under the acid-catalyzed hydration conditions and Markovnikov addition of water across the double bond. The acid-catalyzed hydration proceeds via a carbocation and is non-stereospecific. Hydroboration can be accomplished with borohydride THF complex as well as a reagent known as diborane. Take a moment now to work out the products of the following three reaction sequences. For each of these sequences, the product is the anti-Markovnikov alcohol. For the second and the third example, the major product arises from the stereoselectivity and stereospecificity of the borohydride oxidation sequence. Be sure that you can rationalize the formation of these major products. For this last exercise, choose the appropriate reagents for each of the following transformations. Pause the video and write down your answers. Choosing the appropriate reaction conditions for the hydration of alkenes requires a fundamental understanding of Markovnikov and anti-Markovnikov reactions.